Well, we're working on solving absolute value inequalities, and this time we're going to look at greater than absolute value inequalities. Now recall, when we're dealing with less than, that phonetically sounds like and, less than, less than, and when we're dealing with greater, well, that phonetically sounds like an or statement, greater, greater, greater. And so it's going to function like an or statement. We're still going to set up two cases, but now we're looking at the union, not just the intersection. When we're doing less than, we're looking at the intersection of our solution set. And when we're looking at greater than, we're looking at the union. So let's start, we'll start over here, set up our first case. So we got 2k plus 1 is greater than 7. We're going to subtract 1 from both sides. It's going to leave us with 2k is greater than 7 minus 1 is 6. Divides both sides by 2, and we got k is greater than 3, case 1. Now, when we do case 2, remember we got 2k plus 1. And not only are we going to make this 7 a negative 7, but we're also going to flip that inequality. So now it's 2k plus 1 is less than negative 7. Again, we're going to subtract 1 from both sides. And we're going to have 2k is less than negative 8. Divide both sides by 2, and k is less than negative 4. Now let's put this on a number line out here. And let's say that this is negative 4. Let's put 0 right about here. And let's put 3 out here. All right, let's graph this case first. K is greater than 3. Well, we'd have an open dot on 3, and it would continue off in this direction here. And let's see. In our second case, we'd have an open dot at negative 4, less than, and it would take off over here. Now, if we wanted to check to see if our solution is correct, let's choose a point on this interval right here. Let's say we choose positive 4, and let's plug in 4 for k right here. Well, 2 times 4 is 8, and 8 plus 1 is 9. And so 9 is in fact greater than 7. That's a true statement. Absolute value of 9 is greater than 7. And let's pick a point right here. Let's say negative 5. Let's plug it in for k. And so if we had absolute value of 2, let me do that in a different color. If I do it up there. Let's say absolute value of 2 times negative 5 plus 1 greater than 7. Well, let's see, 2 times negative 5 is negative 10, plus 1 is negative 9. But the absolute value of negative 9 is 9, and 9 is greater than 7. So that's true. That checks. That checks. What if we pick 0? Let's pick a point that's not in our set. It's not in the union of our set. So let's put in 0 for k. So we got the absolute value of 2 times 0 plus 1 greater than 7. Well, 2 times 0 is 0. So then we'd have the absolute value of 1 is greater than 7, or 1 being greater than 7. And that is not true. And so that fails. And so then we would write in interval notation, we would say k such that k is less than negative 4, or k is greater than 3. Close our bracket, and shazam, that one's done. Now let's look at one other here in this example. I'm going to skip to the next slide. All right, so now we got the absolute value of r minus 6 is greater than or equal to negative 5. And we might see this negative 5 and say, well, no, that can't be. But let's see what in fact we do get. Let's set up our two cases. I got r minus 6 is greater than or equal to negative 5. I'm going to add 6 to both sides so that r is greater than or equal to 1, case 1. Let's set up case 2. So I got r minus 6. Now I'm going to flip the inequality so it's less than or equal to positive 5. We're going to add 6 to both sides, and so r is less than or equal to 11 when I add 6 to both sides. Now let's put this on a number line. And let's say we're going to say it's negative 1, and here is 0, here is 1, and out here we're going to say is 11. All right, so if we graph this scenario here on the left, r is greater than or equal to 1, well, I got a closed dot, and my graph is going to head this way all the way out to infinity. Now, what about when I graph the second case? R is less than or equal to 11. Well, again, I'm going to have a closed dot, and my graph is headed all the way this way. And so what's the union of my two solutions? Well, if I look at this number line, this one's going from 1 to infinity, and this one's going from 11 to negative infinity. And so it's all real numbers. And so then I could say r such that r is a real number. In other words, any number for r would satisfy this equation, this inequality. Gets tricky sometimes.